Okay, we're given two trig functions for which we're supposed to find critical numbers. Here's the first one. Note that x is supposed to be between 0 and pi over 3. So to find the critical numbers, we'll set the first derivative equal to 0. Here's the first derivative. You might want to think of sine squared of 6x to look like this, because that helps to visualize the power rule. Bring the 2 down front, sine of 6x, reduce the exponent by 1. But then you have to use the chain rule, multiply derivative of the inside. But the derivative of sine is cosine. And then we got to apply the chain rule again and multiply by the derivative of the inside. So there is the derivative of that first term right there, which simplifies to 12 sine 6x cosine 6x. And the derivative of cosine 6x is negative sine 6x times 6, chain rule. Okay, so there's your derivative. We want to know, when does that equal 0? Note that you can factor out a 6 sine of 6x from both terms, which is what I've done here. Using the zero product property, this is equal to 0 when this factor equals 0, which I've looked at right here, or when that factor equals 0 over here. So working down the left side, if the sine of 6x equals 0, 6x is the angle that has a sine of 0, which means 6x is 0 plus k pi, where k is any integer. So if we divide by 6, we'll get x. And then we can say what values of k are going to give me values for x that are in the interval from 0 to pi over 3. And there really is only one, and that's when k equals 1. If k is 0, we're outside this interval. We're below 0. We're actually equal to 0. If k is negative, we're less than 0. K is 1, we're pi over 6. K over 2, we're at pi over 3, which is, again, an endpoint not included. For this one, solve for cosine of 6x, we get 1/2. So 6x is the angle that has a cosine of 1/2. That happens at pi over 3 or negative pi over 3. And then you can add on any multiple of 2 pi to those values and end up with the same coterminal. So if we divide everything by 6, we get pi over 18 plus k pi over 3, or negative pi over 18 plus k pi over 3. If we do some tests, we see that when k is less than 0, we don't get angles in the interval. When k equals 0, from this first possibility, we get pi over 18. When we let k equal 1, we use this guy. We get negative pi over 18 plus 6 pi over 18, 5 pi over 18. After that, if k equals 2, we move outside the interval from 0 to pi over 3. Here's the graph of that function. On the interval from 0 to pi over 3, there's your critical numbers. That's where the slopes of the tangent lines are 0. So there's your critical numbers right there. On board 2, I've done a similar thing for this function, although I've replaced theta with tangent of theta on the whiteboard. The derivative is 2 secant tangent plus secant squared. Set that equal to 0, factor out a secant of x. That equals 0 when this factor equals 0 or when this binomial equals 0. This secant of x can never equal 0, so we don't have to worry about that one. To solve this equation, probably converting to sines and cosines does the job. I think if I move this picture to the right, no, never mind. I do have a comment out here that the cosine of x cannot equal 0 because I would be dividing by 0. So multiplying every term by cosine of x, we're reduced to this. Sine of x equals negative 1/2. X is the angle that has a sine of negative 1/2. In the first revolution around the unit circle, those are these two guys. Can add on multiples of 2k pi, and then test what values of k give us angles that are between 14 pi and 16 pi. And there's only two of them. If you let k equal 7, we get 15 and a sixth pi, or 91 pi over 6, horizontal tangent line, or 95 pi over 6, 15 and 5/6 pi. There's another horizontal tangent line. My guess is there might be another one there, but that's at 14 pi, not included in the open interval. There you go. Hope that helped. If you have any questions, post a comment.